The Sun, our life-giving star, is a tempestuous celestial body. It undergoes an 11-year cycle of activity, marked by periods of calm and intense activity. We are witnessing the dawn of solar cycle 25, a period of heightened solar activity known as the solar maximum. This cycle is proving to be more potent than anticipated. As the Sun reaches its solar maximum, its magnetic field undergoes a dramatic reversal. This reversal has significant implications for our planet. It heralds a period of increased solar activity, characterized by frequent and powerful solar storms. These storms pose a significant challenge to our technology-dependent world. The Sun's magnetic field acts as a protective barrier against space radiation. During a magnetic field reversal, this barrier weakens, allowing more solar radiation to escape. This increase in radiation has scientists and engineers on high alert. We are at a crucial juncture in our understanding and preparedness for solar events. The Sun's fury, unleashed in the form of solar storms, has the potential to disrupt our lives. Understanding these solar events and their impact is paramount as we venture further into the age of solar maximum. Solar storms, often visualized as spectacular auroras illuminating the night sky, are far more than celestial light shows. They are powerful bursts of energy and charged particles ejected from the Sun, capable of wreaking havoc on our technological infrastructure. These storms originate from sunspots, cooler, darker regions on the Sun's surface that harbor intense magnetic activity. The energy stored within these magnetic fields can be released suddenly, resulting in solar flares and coronal mass ejections, or CMEs. Solar flares are intense bursts of radiation, while CMEs are massive eruptions of plasma and magnetic fields. Both phenomena can have significant impacts on Earth. When these charged particles from solar storms reach Earth, they interact with our planet's magnetic field, generating geomagnetic storms. These storms can disrupt radio communications, GPS navigation systems, and satellite operations. The increasing frequency and intensity of solar storms in recent years have highlighted the vulnerability of our technology-dependent world. The impact of these storms is not limited to space. They can induce electric currents in power grids, leading to widespread blackouts. The delicate electronics in our satellites and even ground-based technologies are susceptible to damage from these solar outbursts. As we become increasingly reliant on technology, our vulnerability to these solar events grows. Elon Musk, the visionary entrepreneur behind SpaceX and its Starlink satellite internet constellation, has voiced concerns about the vulnerability of satellites to solar storms. His concerns stem from the impact of recent solar events on Starlink satellites, offering a stark reminder of the very real threat posed by the Sun's fury. Starlink, with its thousands of satellites in low Earth orbit, aims to provide global internet coverage. However, this ambitious project faces a significant challenge: the increasing intensity of solar storms. Musk revealed that the stress curves of Starlink satellites indicate they barely withstood the onslaught of recent solar bombardment. This revelation underscores the vulnerability of satellites, not just those belonging to Starlink, but all orbiting spacecraft. Satellites are essential for communication, navigation, Earth observation, and scientific research. Damage to or loss of these satellites due to solar storms could have cascading effects on our daily lives and global economy. The challenges faced by Starlink serve as a wake-up call. As we venture further into the age of satellite mega-constellations, ensuring their resilience against solar storms becomes paramount. Investing in robust satellite design, protective measures, and redundancy systems will be crucial to maintaining the integrity of our space-based infrastructure. NASA, at the forefront of space exploration and research, has been issuing frequent warnings about the increasing dangers posed by solar activity. These warnings, often accompanied by stunning images of solar flares and CMEs captured by solar observatories, highlight the agency's growing concern about the potential impact of these events on both space missions and life on Earth. One of NASA's primary concerns is the safety of astronauts aboard the International Space Station, or ISS. The ISS, orbiting Earth at an altitude of approximately 400 kilometers, is directly exposed to the harsh radiation from solar storms. While the station is equipped with some shielding, intense solar events can still pose a significant risk to the health of astronauts. Beyond the ISS, NASA relies heavily on a vast network of satellites for communication, navigation, and scientific research. These satellites are equally vulnerable to solar storms. Damage to or loss of these critical assets could jeopardize ongoing missions, hinder scientific discoveries, and disrupt communication networks on Earth. NASA's warnings serve as a call to action. They underscore the need for increased preparedness, improved forecasting models, and the development of mitigation strategies to protect our astronauts, satellites, and ground-based infrastructure from the Sun's unpredictable fury. Section 5. The year 2024, a prelude to solar maximum. The year 2024 will be etched in the annals of solar astronomy as a year of unprecedented solar activity, a prelude to the peak of solar cycle 25. Throughout the year, a series of significant solar events unfolded, showcasing the immense power of our sun and its potential to disrupt life on Earth. One of the most notable events was the appearance of active region 3664, a colossal sunspot that dwarfed Earth in size, in May 2024. This behemoth sunspot, spanning 17 times the diameter of our planet, unleashed a barrage of solar flares and CMEs, some directed towards Earth. As the year progressed, the frequency and intensity of solar storms continued to escalate. In October 2024, an X9.5- class solar flare, the most powerful in years, erupted from the sun, sending shockwaves through the scientific community. This flare, luckily not aimed directly at Earth, served as a stark reminder of the potential for even more powerful events to occur. These events, while captivating to observe, highlighted the very real threat posed by solar storms. They underscored the need for continuous monitoring, accurate forecasting, and robust mitigation strategies to protect our technological infrastructure and way of life. Section 6. Echoes of the Past, the Carrington Event. In the annals of solar history, the Carrington Event of 1859 stands as a stark reminder of the awe-inspiring power of the sun and the potential for devastation when its fury is unleashed upon Earth. This event, the most powerful geomagnetic storm ever recorded, serves as a benchmark against which we measure the potential impact of future solar storms. On September 1, 1859, astronomers Richard Carrington and Richard Hodgson independently observed a blinding white light flash from a sunspot group on the sun. This event, now known to be a massive solar flare, was followed by a coronal mass ejection that hurtled towards Earth at extraordinary speed. When this CME impacted Earth's magnetic field, it triggered a geomagnetic storm of unprecedented intensity. Auroras, typically visible only at high latitudes, were reported as far south as the Caribbean and Hawaii. Telegraph systems worldwide went haywire, with some operators reporting electric shocks and fires. While the world in 1859 was far less reliant on technology than it is today, the Carrington event still caused widespread disruption. Today, a similar event could have catastrophic consequences, potentially crippling power grids, disrupting communication networks, and causing trillions of dollars in damage. Section 7. Earth's Magnetic Shield, a guardian under threat. In the face of the sun's relentless bombardment of charged particles, Earth is not defenseless. Our planet has a magnetic field generated deep within its core, deflecting most of the sun's harmful radiation. This magnetic field acts as a shield, deflecting the solar wind around our planet. However, this shield is not impenetrable. During intense solar storms, the solar wind can breach the magnetosphere. This interaction causes auroras. However, these interactions can also disrupt power grids and communications. There is growing concern about the weakening of Earth's magnetic field. Scientists believe this could be a precursor to a geomagnetic reversal. During a reversal, the magnetic field weakens significantly, leaving Earth vulnerable to solar radiation. Section 8. Preparing for the inevitable, a race against time. As we delve deeper into the age of solar maximum and the increasing frequency of intense solar storms, the need to prepare for the inevitable consequences becomes ever more pressing. Our reliance on technology has made us increasingly vulnerable to the sun's unpredictable outbursts, and mitigating this vulnerability requires a multifaceted approach. One crucial aspect of preparedness is improving our ability to forecast solar storms. Just as meteorologists track weather patterns on Earth, space weather forecasters monitor the sun's activity using a network of ground-based and space-based observatories. However, predicting the precise timing and intensity of solar storms remains a challenge. Investing in research and development of more accurate forecasting models is paramount. Advanced warning systems can provide crucial time for power grid operators to take preventative measures, satellite operators to adjust orbits, and airlines to reroute flights, minimizing the potential impact of a solar storm. Beyond forecasting, hardening our infrastructure against the effects of solar storms is essential. This includes developing more resilient power grids, designing satellites with better radiation shielding, and creating backup communication systems that are less susceptible to solar interference. Section 9. The Future of Solar Forecasting, Towards a Safer Tomorrow. The future of our technological civilization hinges on our ability to understand, predict, and mitigate the effects of solar storms. As we venture further into the era of increased solar activity, the need for accurate and timely solar forecasting becomes paramount. Thankfully, advancements in technology and our understanding of the sun offer a glimmer of hope. Scientists are constantly working to improve solar forecasting models, incorporating data from a growing network of space-based and ground-based observatories. These observatories, equipped with advanced sensors, provide a constant stream of information about the sun's activity, allowing scientists to track sunspot formation, solar flare eruptions, and coronal mass ejections in real time. Artificial intelligence and machine learning are also playing an increasingly important role in solar forecasting. These technologies can analyze vast amounts of data from solar observatories, identify patterns, and make predictions about future solar events with increasing accuracy. While we may never be able to completely prevent solar storms, the ability to predict them with greater accuracy and provide timely warnings will be crucial in mitigating their impact. This will require continued investment in research, development of advanced technologies, and international collaboration to ensure a safer and more resilient future for our technology-dependent world.